Hi, everybody. My name is Mauricio Arredondo. I'm a postdoctoral research fellow at the University of Alberta. I also work in the Smart Lab, led by Professor Rafiq Ahmad. Our work is titled Mobility Add Multi-Tool end-effector for picking and nailing applications in robotic timber assembly. And let me start with the things we know. Timber assembly plays a vital role in the construction industry, especially in countries like Canada. Timber assembly is particularly well suited for robotic fabrication. Currently, robotic timber assembly is predominantly carried out in off-site facilities. While these factories are advancing towards full automation, there is a need to develop robotic manufacturing solutions closer to the construction sites. For instance, transportable robotic manufacturing cells. But this type of cells face some challenge, such as the amount of tasks involved and the need to perform these tasks simultaneously. Available solutions include incorporate additional automate device into the manufacturing cells and equip the robots with the ability to perform multiple tasks by employing tool changers and multi-tool end-effectors. And these are great options. We are actually using multi-tool end-effectors. As you can see here in figure 1, there is a gripper nailing end-effector installed on the KUKA robot that we have in the Smart Lab. While these solutions improve efficiency, they fail to address the fundamental issue of perform multiple tasks simultaneously. So in applications such as nailing, the robot may still need external devices to complete the process. And this work is trying to deal with this problem. Instead of using external device, we want to make the robot able to hold and nail timber elements at the same time. So the concept of mobility at multi-tool end-effector is introduced. This end-effector enables simultaneous execution of picking and nailing with the ability to modify nails position and orientation. It is designed using 1 degree of freedom closed-loop linkages driven by linear actuators, which may allow an easy control integration and provide structural stability, characteristics of this type of linkage. The general structure is shown in figure 2. It's composed of 4 main modules: gripping, linear translation, rotation, and height variation. The main objective of this work is to present the end-effector concept and its operational principles without delving into detailed technical analysis for now. So module 1, gripping, is shown in figure 3. It is composed of 2 grippers symmetrically positioned along the end-effector's y-axis. This module allows the end-effector to pick and hold timber elements during the nailing process. Module 2, linear translation, is shown in figure 4. It utilizes a double Poisselier planar mechanism. The Poisselier mechanism is a classic straight line generator with 1 degree of freedom. By connecting 2 Poisselier mechanisms in parallel, as shown in figure 4A, it not only generates a straight line motion, but a straight line rigid body translation, which allows to move the nail gun linearly parallel to the y-axis over the gripped timber element without on-the-side rotations. The double mechanism design with the dimensions used in this work allow a linear displacement of 700 millimeters with an input-output ratio of 3:1, which means that the nail gun can move 3 times the displacement of the input linear actuator. Module 3, rotation, is shown in figure 6. It is based on 2 parallel forward planar mechanisms, the classic ones. The complete arrangement is 1 degree of freedom. And in this mechanism, the nail gun is attached to link 3, and 2 independent variants are proposed. 1 to perform rotation about y-axis and 1 to perform rotation about x-axis. Module 4, height variation, shown in figure 5, consists of a nail gun and a linear actuator connected by a linear track. This module is used to modify the distance between the nail gun and the gripped timber elements. Now let's see the application examples. This section provides visual demonstration of the end-effector functionality in real timber nailing process. 2 robots equipped with the end-effectors were animated during the fabrication of 3 timber nail structures: straight on plane, rotate on plane, and rotate off plane. Let's consider these 2 robots are working alone with no other external device, just the robots with the objective to manufacture these 3 timber nail structures. So the manufacturing process consists of one of the robots picking, holding, and nailing the timber elements, while the other robot is just providing additional studs during the process. Let's see the animations. First, straight on plane. Module 1 is holding the timber element, and Module 2 is moving the nail gun to the next position. Module 4 is approaching the nail gun to the timber element to perform the process, the nailing process. Okay. Next is the rotate on plane. Again, Module 1 is holding the timber element, and Module 2 is moving the nail gun to the next position. But this time, Module 3 is rotating the nail gun to align the nails with the timber elements below. Finally, we have rotate of plane. And this is very similar to the previous one, with the difference that now we are using the other variant of Module 3 to perform rotations of plane, but again, to align the nails with the timber elements below. Okay, to summarize this work, the proposed end-effectors have some advantages, such as optimization of space, time, and robotic resources. Also, due to its 1 degree of freedom mechanism design, it is easy to control and provide high force transmission and structural stability. Also, due to its modular design, it's flexible to adjust to different scenarios, and of course, eliminate the need for other external devices. On the other hand, there are also some limitations identified, such as questionable accuracy due to its custom-made nature, something that happens to all custom-made machines at the beginning. Also, the implementation can be complex due to the high number of parts and the need for technical validations. And of course, the need to develop the control and the integration into the robotic process. Maybe the control won't be too difficult, but we need to do it because at the end of the day, we're adding motion, we're adding degrees of freedom to a robotic system. So as a future work, we plan to optimize the end-effector motion, dimensions, and working space, do technical validations, manufacture and assembly, implementation, and experimental tests. To conclude, the concept of mobility at multi-tool end-effector presented in this work goes beyond the additional mobility and multi-tooling. It emphasizes equipping the end-effector with the necessary capabilities to perform tasks independently of the robot motion. This independence may significantly advance the automation of timber assembly, offering a compact, efficient, and versatile solution for robotic systems. And this is the end of my presentation. Here are my contact details and the website of my research group. Thank you for your attention.